Okay, we're going to continue on here. We've been talking about transition metals and coordination compounds. And again, as we talked about mainly last time, we have coordination compounds, and they're basically made up of two things. They're made up of a complex ion and a counter ion. And again, as we talked about, you can kind of think of them as sort of like ionic compounds. There's a positive and a negative. And just like ionic compounds and nomenclature with ionic compounds, both with formula and also name, we do go positive guy first, followed by the negative. And we can have a complex ion that is positively charged, and we could have one that is negatively charged in terms of the counter ion. Or the other option is pretty much the opposite of that. Our counter ion here is going to be positive, and our complex ion will be negative. And when we talk about a complex ion, that basically is a metal in the middle. And usually it's a transition metal that's positively charged, which means it acts really well as like a Lewis acid, something that's able to accept electrons. Attached to it is a bunch of what are referred to as ligands. And ligands are molecules or atoms that are basically Lewis bases. And again, a Lewis base is something that can donate a pair of electrons. And in this particular case, the NH3 is our Lewis base, and our ligand, again, is a polar molecule. It's got some non-bonding electrons on a very electronegative atom like nitrogen, oxygen, or maybe even fluorine. And it is those guys that are going to kind of donate those electrons over to, for example, the cobalt that has a positive charge and is really more electron deficient in this case. That also led us to the idea of coordination number. And coordination number, remember, is not necessarily just the number of ligands that are attached, but it's actually how many atoms are directly attached to the metal. In this case, the nitrogen in each of these ammonias are the ones that are going to attach there to the metal. And that means ammonia, for example, will always attach to the nitrogen and only the nitrogen. And that is what is referred to as being a monodentate ligand, which means it will only attach in one atom per molecule. So the coordination number on this particular one would be 6 because, again, there are 6 nitrogens attached to the central metal. Remember that not all ligands are monodentate. There are ones that do attach in multiple places per molecule. We talked about two main ones, and that was EN, which is ethyl endyl diamine, and that looks something like this. And it has two amine groups on it, hence the diamine part of the name. And at both of those nitrogens on those amine groups has the ability basically to attach to that metal ion. And you basically get kind of like a 2-for-1 deal on that in terms of coordination number. So for every molecule of ethyl endyl diamine or EN, you basically get two sort of coordination numbers per molecule. So if you had two of those attached to a metal ion, the coordination number would not be 2, but it would actually be 4 in this case, as again, each of these nitrogens would also attach to give you 4 total. Another very common sort of bidentate is oxalate, C2O42 minus. Again, if you draw sort of oxalate, it will look something like this. And it's at actually each of these single bonded oxygens that actually carry a -1 formal charge. That is where they will bind into the metal. So again, you get kind of a 2-for-1 action. There are some that could do kind of 3, for example. We saw one that looks just like this, but it has one more sort of NH2 group on it and a couple more carbons. And that's a triene, which can bond in 3 places. There's that EDTA, which can bond in like 6 places per one molecule. So the coordination number is not always, as I mentioned before, sort of the subscript in terms of how many ligands you have. It is dependent also on the type of ligands they are, whether they're monodentate, bidentate, or polydentate. Now we got into some naming, and there's some interesting rules in terms of naming, but typically when we do write coordination compounds, uh, typically speaking, the complex ion is a lot of times put in brackets. And again, you could have your counter ion either at the beginning of it or at the end, depending if your complex ion is positive or negative. Now, when we got into naming, there's a bunch of rules, and we kind of went over there at the end, but since we'll just kind of browse through this one more time. I remember that, again, a cation is always before the anion, and again, that's both in name and formula. We do the alphabetical order of the ligands, regardless of prefix. So if there is more than one of the same ligand within the molecule, we do use a prefix like di for 2, tri for 3, tetra for 4. But when we go alphabetical order in terms of the ligands, we ignore the prefix. When we name the complex ion part of the name, because there will be, especially with coordination compounds, there will be a complex ion part of the name and also a counter ion part of the name. In the complex ion part of the name, the metal always comes at the end of that part of the name. And remember that some of the ligands do have some different names. So we have aqua for water, carbonyl, amine. As I mentioned before, di, tri, tetra, penta, hexa is used for more than one of the same ligand. If again, the ligand itself within the name of the ligand actually has one of those prefixes, then we move over to bis for 2, tris for 3, tetrakis for 4, and we kind of go with those ligands. And again, an example of that would be En. The ethyl endyl diamine has the di in the name. We also do write a Roman numeral for each of the metal in terms of their charges. And unlike sort of normal nomenclature, even things that sort of have fixed charges, we don't normally write a Roman numeral for. We do write in this type of naming. So things like silver does get like the Roman numeral 1. And as I also mentioned, I think last time as well, it is possible you could come up with a neutral sort of metal. So people will sometimes also put kind of parentheses and a 0 in there to indicate something that is neutral. Now, one of the interesting things about these naming is it has to do whether or not the complex ion is positive or negative. And if the complex ion part of the name is a positive ion, basically what that means is you could just use the regular name for the metal like you normally would, like iron is iron, copper is copper, cobalt is cobalt. If it is a negative complex ion part of your compound, then you actually have to go kind of like an old school type name, and those guys usually end in ate at the end of it. So again, instead of iron, it would be ferrate. Instead of copper, it would be cuprate, zincate, and most of those do end with an ate, and kind of that older sort of school name on terms of the metal. Any questions on any of that there? Now, we went through some of these tables, I think, last time as well, but just to review, since we were looking at them, again, in terms of the halogens, fluoro, chloral, bromo, iodo are very commonly, much like how you do it in organic. Hydroxo there for hydroxide, cyano there for cyanide. And then, as you can see, NH3 is amine, aqua for water, and again, some other sort of names. And here's a few of those sort of older school names for the metals. Again, we would use these in a situation where our complex ion is negative overall. So you can see ferrate, cuprate, plumate, argentate, arurate, and stannate. And here's another list again of some of those other ones: carbonate, carbonato, oxalato for oxalate, and some other ones as well. All right, any questions on any of that stuff there we talked about last time? All right, so I think we went back and did kind of the names of the two that we did the oxidation numbers on. So I think this is where we left off. So why don't you give the name for this particular one here? Also figure out the coordination number. And okay, so let's take a look at this one. So once again, when we kind of look at the setup here of this coordination compound, once again, in the brackets is our complex ion. And up in front here in this particular case would be our counter ion. And again, probably the first thing you usually want to do is probably figure out what is the oxidation state on the metal. That is a part of our complex ion. So when we take a look at this, this is oxalate, which is a -2 charge. There's 3 of them. That's a -6. My potassium is +1, but there's 3 of them, which gives me a +3. So basically I got a +3 and a -6, and that's going to leave me a -3 left over. So again, here to balance out that to 0, which is what my overall charge is, the chromium here is going to be a +3 oxidation state. Now, when we look at this here, the coordination number is how much in this one? Coordination number is 6 in this case, yes. And that is because there are 3 of these oxalates, and oxalate again is bidentate, which means each one will bind in 2 places per molecule. So 2 times 3 gives you a coordination number of 6. Once again, not always, especially if it's bidentate or polydentate, not going to always be that number that's on the bottom. All right, so a couple other things that we know right off the bat here. My counter ion comes first, which means it's positive. And in this particular case, my complex ion comes second. So I know that it's negative. Again, it works just like an ionic compound, positive and then negative. So as I mentioned the other day, I think when we were wrapping it up, in terms of the counter ion, the good news is you pretty much just use the name of it, and it really doesn't matter how many you have. So for our K, we will use potassium, and it doesn't matter that there's 3 of them. We don't use prefixes or anything like that with the metal. And again, normally for the counter ion, it's just going to be kind of the whole name. Now, we do have 3 of the oxalates here. And once again, when we look at our little chart, oxalate is right here, and that is oxalato is the name for oxalate here. So we do have 3, which is the prefix is tri-oxalato. And that is what we would then start with, since that is the only ligands present, trioxalato. And here, because our complex ion is negative, we will use kind of the older school name, if you will, the one that ends with ATE. So instead of chromium, this is going to be chromate, and this is going to be Roman numeral 3 in this case, again, for the +3 charge that is here. And as we talked about last time, again, the metal name always should come at the last part of the complex ion name, which it does in this case. As I mentioned maybe before, oxalate is an interesting one. People will also, even though oxalato doesn't necessarily, or oxalate doesn't necessarily have maybe a prefix in it, people will sometimes use the other prefix with it, and would call this tris oxalato chromate 3. So oxalate is kind of a common one that they kind of like to use. Sometimes that other prefix rather than tri. For oxalate, I'll take either one, to be honest with you, but you will sometimes see sort of the tris used in this particular case. Any questions on that one there? All right, let's try a couple more here. Top one, we're going to go name. Bottom one, we're going to go formula. So write the proper name up on top and the proper formula there on the bottom. Okay, so let's take a look and see how we're doing on this. So first one, we're looking for a name. So once again, typically speaking, in the brackets, it's going to be our complex ion. That would mean our Cl here is our counter ion. And once again, we can kind of figure out our oxidation state on our metal and our complex ion. We have 4 waters. Each water is no charge, so that's 0. The Cl's inside the complex ion, they're each -1, and there's 2 of them, which would give us a -2 overall. On the outside, we have 1 chloride, which would also be -1. So altogether there, we got kind of like a -3 going on. So the chromium here would have to be +3 in this particular case. In terms of our coordination number in this case, our coordination number in this case would also be 6. There are 4 waters, each bind at 1 oxygen per water, and there are 2 Cl's that are attached to it. So that's a grand total of 6 atoms that are directly attached to the metal in the middle of our complex ion. That would give us a coordination number, once again, here of 6. We also, again, know based on sort of the arrangement of the formula here that our complex ion is positive because it comes first, and our counter ion is negative because it comes second. That also tells us that basically we could just use the regular name for the metal, chromium here. We don't have to use chromate in this case. So we're ready to kind of put things together. We have 4 waters, so the prefix for 4 is tetra, and water is aquo or aqua, your choice. The prefix for 2 is di, and we have 2 chlorines, so that's a dichloral that's happening there. By the way, we do not use the prefix mono in this type of naming with the complex ion. So if you just have one ligand by itself, you would just use the ligand name by itself, no like mono or anything like that. And that takes care of all of our ligands. So we're going to go alphabetical order here. And once again, we are going to look at alphabetical order of the ligand names and not the prefixes. So we are comparing A for aqua to C for chloral, and A should come first here. So again, we ignore the prefixes in the alphabetical part of it. So this is going to be a tetra aqua dichloral. Once again, we could use the whole name of the metal because it's positive. Chromium, Roman numeral 3 because of the charge on it. And now we are left with really our counter ion name. And our counter ion name is named just like normal. So if you had an ionic compound Cl at the end of it, that would be our friend chloride. So this would be tetraaquo dichloral chromium 3 chloride. Here, when we look at just the complex ion part, it has an overall charge here of +3, 0, -2. Has an overall charge of +1, which is, again, why we have just one counter ion present, the Cl- to balance it out. By the way, if you had just this formula here without the counter ion present, this would be the name, and then you would just put ion at the end of it. So again, if you did not have the counter ion present in this case, you would name it the same way, just kind of put ion at the end and not name the counter ion in this case. So if you had that, that would be like this guy here. Any questions on that there? All right, in this case, we do have the name given to us, so we're going to kind of put it together correctly, hopefully. So tris ethyl endyl diamine, that is that one with the 2 carbons and the 2 NH2 groups, and tris means 3. So we basically got this going on. Again, the EN abbreviation is used both in the formula and the name very commonly. We have cobalt with a +2 charge there, and we got a cobalt going on. So through this part here, this is my complex ion part. I know this is the end of the complex ion part because the metal comes at the end of that name. So a reminder that the metal always comes at the end of the complex ion part. That's why up here, metal comes at the end of the complex ion part of the name. Not the actual end of the name itself, but at the end of the complex ion part of the name is when the metal should come. So I can actually build my little complex ion here. I got me a cobalt, I got me En and 3 of them. And since the En is 0 and neutral, The entire charge on this guy is going to be a +2 from the cobalt in this case. That's really important to know because here, this is my counter ion, and my counter ion is sulfate, which has a -2 charge. So in this particular case, we actually just need one of each of them to balance it out, and you will end up with COEN3SO4 as the formula here. Any questions on that one? By the way, the coordination number on this one is 6 as well. Again, 3 of the ENs, they're both bidentate, so that's 2 times 3 gives you 6 in this particular case. Yeah. And again, you would have 6 nitrogens attached to the metal in the middle. Any questions on that there? Obviously, you can see here to the left some of the other names for some metals and how you kind of use the negative ion version of it. Let's try a couple more here. Maybe let's do some names on each of these. Okay, let's take a look. So we'll take here, again, complex ion part there. And our counter ion here. And looking at our oxidation state, so NH3 is 0. That is a -1 for the chlorine within the complex ion. That's a -1. There's 2 of them, gives you a -2 for the chlorides on the outside. So here our cobalt is going to be +3 in this particular case. Once again, here coordination number is also 6. We got 5 NH3s and 1 Cl attached to the metal. Each of those are monodentate. Once again, the coordination number is not always going to be 6, by the way. So we also can see our complex ion is positive as it comes first. Our counter is negative. So we do have 5 of the ammonia there. So that's pentamine. We have 1 chloride inside the complex ion, so that's going to be a chloral. Again, we do not use mono here or anything like that. And that leaves us our metal, which since it is positive, will be just a regular name there. So that's going to be cobalt. And it's going to be Roman numeral 3 because of that. And now on the outside, again, regardless of how many of those counter ions you got, you're just going to use the proper name for it. And that proper name with it coming second would be chloride in this case. So pentamine chloral cobalt 3 chloride. Any questions on that name there? Looking at the next one, once again, this is going to be our complex ion. This is going to be our counter. And again, we can see our counter is positive and our complex ion is going to be negative as it is rolling through second. So figuring out our iron charge, that is cyanide, which is -1, and there's 6 of them. That's -6. The potassium in the front is +1, and there's 3 of them, so that's +3. So +3 -6 will give us a +3 for the iron. By the way, as well, the charge on the metal is not always going to be +3. It just happens to be a number of these here in this case. All right, so counter ion we could just name. So that's going to be potassium. Here we have now our complex ion part. We got 6. So the prefix for 6 is hexa. Cyanide is cyano. So that's hexacyano. And here, because our complex ion, once again, is negative, we have to go with kind of the older school name. So instead of iron, this is going to be a ferrate situation. And again, we're going to use our Roman numeral for 3 in this particular case. So potassium hexacyanoferrate 3. Coordination number on this guy also 6, as cyanide is unidentate or monodentate in this particular case. Any question on that name there? All right, 2 more here. We'll do formulas on this. So give the proper formulas for each of these names. All right, so again, in this case, we just want to kind of get the pieces and kind of put it together. Usually you might want to start with your complex ion part, which for me here on the first one, I know that this is my complex ion part because the metal part should always come at the end of it where the Roman numeral is. So I do know my complex ion is positive in this case, and my chloride is going to act as my counter ion in this case, which is going to be negative. So looking at the complex ion part, triamine, that amine is NH3, and tri means I got 3 of them. Bromol is bromine, and I just got one of them as there's no prefix with it. And I have a platinum that is a +2 charge because of that. So basically just putting together the complex ion part, I will have my PT, I will have my NH3 to the 3, and I'll have my Br. Now, figuring out the charge here, my complex ion is important. I know it should be positive. Again, this is going to be 0. That's going to be +2, and that's going to be -1. That means overall, the actual charge here on my complex ion is a +1 charge. And that's important for my balancing with my counter ion here, which is Cl minus, and that means I just need one of those guys. So when I put that all together, I do end up with something that looks like this, where the coordination number on this one is actually 4 in this case. 1 bromine and 3 ammonias here in this particular case, as they are all monodentate. Any questions on that one there? All right, taking a look at the next one here. This is my complex ion part. I got my Roman numeral there. I got my metal coming at the last part of the name. So this part is my complex ion. That would mean the potassium here is going to be my counter. Also tells me based on the placement there, my counter is going to be positive and my complex ion is going to be negative in this case. I also know my complex ion is going to be negative because the name of the metal is cobaltate, ATE. Doesn't sound very much like cobalt, a little bit does, but it's not obviously cobalt. So here's that older sort of school name. So just building the, again, complex ion part, hexa is 6 and fluoral is fluorine. So we basically got 6 fluorines. Cobaltate is CO, and that is a +3 charge for it. So again, if I sort of built my complex ion part, looks something like this. That's going to be -1, and there's 6 of them. It's -6. The cobalt is +3. That means in this particular case, I am rolling with a -3 on my complex ion. Now to balance that out here, my potassium is group 1, so I don't need 1, I don't need 2, but I do need 3 of those guys to give me a +3 to balance out that -3, and that's going to give me a K3COF6 as my formula in this case. Coordination number here is going to be 6, as there are 6 fluorines attached to the metal in the complex ion. Any questions on naming or writing the formulas there? All right, then let's continue on and talk a little bit more about a couple other things that occur with sort of complex ions, and that are isomers. And isomers are, for the most case, it is something with the same sort of chemical formula, but there's some type of different connection usually. And because of that different connection, it does give some different properties for certain things. And in terms of isomers, there are structural isomers, which have different bonds. And within that sort of group of isomers, there's coordination isomers, which we'll talk about, and also linkage isomers. On the other side, there's also what I refer to as stereoisomers. These have the exact same bonds, but they're arranged differently in sort of three-dimensional space. And because of that, it does give them some different properties. And there's 2 types of stereoisomers. There's geometric isomers, which are sometimes referred to as cis or trans. And there's optical isomers, which have the ability to move plane polarized light one way or the other. So let's take a look at each of these different types of isomers. So this is an example of a coordination isomer. And a coordination isomer, as I mentioned before, is basically the exact same formula. So if you just count up everything that is here, I got one chromium, one chromium. I got 5 NH3s, 5 NH3s. I got a bromine and a bromine and a sulfate and a sulfate. So we have exactly the same stuff, if you will. Now, the difference here in a coordination isomer is in the top one, for example, this is my complex ion here. And what that means is in the top one, I have chromium and I got myself 5 NH3s attached there. And I have the actual sulfate attached as well. And the bromine in this case is my counter ion in this particular case. And what happens in the second case is this is my complex ion. And in the second case, the bromine is no longer a counter ion. It's actually part of the complex ion. So it's attached to the metal in the middle. In this case, we have still our 5 NH3s basically. But now we have the bromine hanging out there. And on the outside, we have our sulfate here, a little +2 action. And we have our sulfate basically moving on the outside there. So the difference with coordination isomers is, again, as you can see, it has really the same components, if you will, really the sort of same formula in terms of what is present. But in one case, one of the ligands is attached, obviously, to the complex ion, and the other guy is the counter ion. And then, obviously, there's a switcheroo there. The one that was originally the ligand is now the counter ion, and the other guy is the ligand. Any questions on that difference there? Now, another type of sort of isomer here is a linkage isomer. And a linkage isomer is pretty much what it sounds like. It is actually how the particular ligand attaches to the metal in the complex ion. And NO2, which is nitrite, is an example of that. So when you have nitrite, not drawn correctly, but just draw with the letters there, it has the ability to attach via the nitrogen, but it could also attach through one of the oxygens as well. So in the top example here, the attachment of that NO2 minus is actually through the nitrogen to the metal in the complex ion. Now we have the exact same ligand here. The only difference is the attachment on the ligand is actually going to happen there at the oxygen rather than the nitrogen. So a linkage isomer, once again, will be pretty much the same formula, but a ligand in there has the ability to attach one atom versus the other, depending on sort of the situation that occurs. Each of those atoms can do that because they both have non-bonding electrons. They also are kind of polar and have a formal charge that allows them to sort of do that. Any questions on linkage isomers? Now, stereoisomers are sort of the other type of isomers, and that gives rise to what are referred to as cis or trans isomers. Cis and trans is something you hear a lot about in organic chemistry, but cis and trans, cis basically means the same side, and trans usually means opposite sides. And in the case of organic chemistry, a lot of times you're talking about kind of a double bond and whether or not something's on the same side or opposite sides of that double bond. In sort of these complex ions, we're talking about sort of same side or opposite side of the plane of the molecule. You know, are they on the same side? They have the same atoms, they have the same bonds, but again, some different bond angles occur. They're very common in square planar complexes. You might remember square planar, expanded octet, the one that kind of makes like a square within the plane, and it's got the two non-bonding electron pairs going through the center. Looks something like this. And here we can see in A, it is cis. So within the plane of the molecule, both of the ammonias are on the same side. Or you could even look at the chlorides if you like as well. They're also on the same side. And again, that would give you your cis isomer. As you can see here, our ammonias are now on opposite sides of each other. You could also, once again, also look at the chlorides are on opposite sides of each other as well. And that would give us our trans. And again, depending on the orientation here, you will get some different properties. Sometimes they will make some different colors and have some other differences in terms of their properties, depending on sort of the arrangement that occurs. This also occurs in a what is sometimes referred to as the octahedral arrangement. If you remember, octahedral also an expanded octet, and it has basically 6 electron pairs, right? 6 bonds around it. And this is also trans and cis. So you can kind of think of our plane of the molecule. And if we look at the chlorides here, one's kind of above the plane and one's below the plane of the molecule. And that, again, as you can maybe see here, would give you your trans isomer. When we look at the next one here, once again, this is sort of the plane of the molecule. And we got our chloride here and our chloride here almost at a 90-degree angle from each other, kind of both on the upper end or the bottom end, depending on which way you're looking at it. That is our cis arrangement in terms of that. So this is sort of our octahedral arrangement in terms of the geometry. And basically trans, usually the groups will be sort of opposite sides, especially in this orientation here, kind of above or below the plane of the molecule in the middle, or they will be kind of on the same side and 90-ish degree sort of orientation in the cis arrangement. Here in the one previous, this is again more of a square planar arrangement in terms of geometry, and here just sort of opposite sides or same side basically of the center guy. Now, optical isomers can have an effect on plane polarized light. Molecules that have a non-superimposable mirror image are what are referred to as a chiral molecule. And the isomers are sometimes referred to as enantiomers. So if a molecule is chiral, a lot of times what that means is if you take that molecule and you put it up to a mirror, and the reflection that occurs within the mirror, if you take that reflection out, it will not be able to be superimposed on top of the original one. So the common example, as we'll probably see here in the next slide, is your hand. You put this hand up to a mirror, you get the other hands facing you, right? And if you take the other hand out of the mirror, you can do as much as twisting and turning as you want without hurting yourself. You will never get them to sit perfectly right. You get the thumbs in the right location, but one's palm up, one palm down, right? Get both palm down, but thumbs are not in the right location. So there's always something that's not going to be in the right location when you have a chiral molecule. Plain polarized light, again, goes through a filter, and there's sort of 2 orientations for it. You could also measure the angle at which it moves it. We're not going to really get too much into that, but you can also measure sort of how much it moves it one way or the other, the rotation of it as it goes through the sample. There's our hands as an example of a chiral molecule. Again, non-superimposable mirror images. You'll sometimes hear achiral, and that is a molecule where if you do take the mirror image of it, you can take it out and it will fit perfectly on top of another. A lot of times you talk about that in terms of, for example, a carbon that has 4 different groups attached to it is usually a chiral carbon and will have a mirror image that does not superimpose. If you have a carbon that does not have 4 different groups, but 2 are alike, it typically will allow you to be able to rotate that mirror image into a way that everything will fit perfectly on top of each other. So here's a couple examples. And again, if we take a look over here, our isomer 1 is identical and cannot be superimposed. And if we take a look sort of at what the difference is, this is our original sort of image down here. And as it gets reflected, you got this guy obviously coming back this way. You have this guy being reflected. And then you have these guys obviously being reflected into the mirror. And basically the difference though that actually occurs in the reflection is this bond here. So within the original molecule, there is a bond between those two guys. And in the reflected image, as that guy goes to the back, it actually is bonded to the guy in the back, which means when you pull them out, these guys are not going to line up nicely in terms of their bond angles. Even if you try to rotate them around, they will not match up with each other here. So that is a mirror image that cannot be superimposed on each other in this particular case. If we take a look at these two here, again, the first one is a trans, which does have a mirror image that can superimpose. So in this particular case, we basically get in the reflection that occurs the exact same connection that occurs. And we don't really make any kind of new bonds within the reflection, which means if you take this mirror image out, you can slap it right on top of that old one and it will fit perfectly on it. Once again, here with our second one, which is our cis, and again, our cis where we have our groups kind of at 90 of each other here. As this gets reflected to the front and this guy gets reflected to the back, we once again are going to be making a sort of different connection from the front bottom there to the back that we again see happening in this front part. And again, with that difference is what's going to make it really not, even with rotation, be allowed to basically sit perfectly on top of each other. And that guy will not be superimposable on this side. A lot of times the cis isomers does that. You get that sort of reflection that kind of creates that little different connection in the mirror image that you don't oftentimes see a lot with trans isomers. So trans isomers, a lot of times, you will get that reflection that can be superimposed. Enantiomers, as I mentioned, are two molecules where mirror images of each other are non-superimposable, and they are chiral. And in some cases, even these guys that, again, have non-superimposable mirror images, they will have some different properties because, again, they are making some different connections within the mirror image, and that will give them some different properties. Like it says here, sometimes within drugs, one is very effective, but that mirror image enantiomer is not so effective. Any questions on isomers there? Next thing we're going to talk about is sort of bonding within these complex ions and sort of what happens with the electrons. And the formation of hybrid orbitals to share electrons, you remember hybrid orbitals, I hope, like sp, right? sp2, sp3, sp3d, sp3d2, right? And the Vesper model doesn't work perfectly well for complex ions. Again, as we've been talking about, we sort of think of this as an interaction, more of a Lewis acid base interaction where we're kind of donating and accepting these d orbital electrons. The hybrid orbitalization used does depend on the ligand. And there are some common sort of geometries associated with complex ions. We have tetrahedral, which is a coordination number of 4. We also have square planar, which is a coordination number of 4 as well. And we also have linear, which is a coordination number of 2 as you go through there. And these are the very common sort of structures associated with our coordination numbers. 2 is linear, kind of like SP, right? And sp3, their tetrahedral, also our expanded one with our square planar, is a coordination number of 4, and octahedral, which is basically a coordination number of 6, right? And if you think about octahedral and Vesper, that is 6 electron pairs and 6 bonds, so that is the octahedral expanded octet arrangement that you talked about probably in the last class. And we do have these sort of geometries that happen here with our complex ions. Now, when we talk about bonding within a complex ion, because typically the metal within the complex ion is a transition metal, those are d electrons, d orbital electrons that are present. And as you may be familiar with, right, there are 5 different d orbitals, and there they are right there. They kind of look like 2 p orbitals together, except with the one with a donut there and a p orbital going through the center. Now, without any ligand present, you will have basically all 5 of those d orbitals will all be basically the same energy. So all 5 of those d orbitals will be of the same energy. What happens though when they start to bond and we do get some ligands attached, we actually get some splitting of those d orbitals. And we get this splitting, for example, here, what we're looking at, by the way, is a coordination number of 6. And this is the octahedral sort of splitting that we are looking at specifically here. And what we end up with is 3 of the d orbitals lower in energy, and we end up with 2 d orbitals higher in energy. And the splitting between the higher orbitals and the lower energy orbitals in the d are what is referred to as crystal field splitting, sometimes just abbreviated with a little triangle as well. And the crystal field splitting is that energy difference that occurs within a orbital, the d orbitals of a transition metal in the presence of ligands. Now, if you remember, what's going to happen in this situation is one of 2 things. Electrons will go into these orbitals, hopefully, as you know, one at a time, right? In Hund's rule, to maximize parallel spin. And then they will come back and pair off in the opposite direction to not violate Pauli's exclusion rule, which means no 2 electrons in the same orbital could have the same 4 quantum numbers, right? And they get away with that because it has different spin, right? MS quantum number plus a half or minus a half going on. So when we get this crystal field splitting, let's just say that this is a really large sort of splitting that occurs in terms of energy. And we have some electrons from our transition metal that we want to distribute. They would go in like so. And then what will happen at this point is they'll go, that looks a little too large for me. I don't really want to go in that direction. So they will rather just fill up the bottom first before they decide, all right, then I'll go up there. Now, we can have this splitting where maybe the difference here is small. And when the electrons will go into these orbitals, they'll go in like normal one at a time and go, that's not too bad. Yeah, we'll just go kind of upwards next instead. And they will kind of feel like normal. And at this point, they'll go back down and pair up on the bottom and then go to the top and pair up. Now, what ends up happening, as you can kind of see in just this little demonstration, is we end up with 2 complex ions that are very different in terms of the electron spins that they have going on. We have one with a lot of unpaired electrons like we have on the left, and we have one with not very many paired electrons or unpaired electrons on the right. And this gives complex ions, which are sometimes referred to as high spin, which has a lot of unpaired electrons, or they will give rise to what is known as a low spin complex, which has a lot more paired electrons, right? So unpaired electrons, paramagnetic, right? Diamagnetic, the electrons pair up with each other in terms of their spin in this situation. Now, you could actually calculate the energy of this splitting by doing an equation that you might be familiar from before. A couple equations, c is equal to the wavelength times the frequency. That is the speed of light. And that is, I'm going to go with 3 times 10 to the 8 meters per second. You can use 2.997 if you like, times 10 to the 8. That is the wavelength in meters. That is the frequency in reciprocal seconds or hertz. And this is the energy is equal to h times the frequency. H is Planck's constant. We'll throw back to the first chapter last semester, maybe the second. A little 6.63 times 10 to the minus 34 joules times seconds. And once again, that is the frequency in reciprocal seconds in this case. And as you might also remember, you can substitute those two equations together and get hc divided by the wavelength. So if you know the wavelength of light, you can figure out the energy associated with it. If you know the frequency, you could also get the energy associated with it. This you might remember as well, right? The old spectrometer master, right? Figure out the maximum absorbance. And what we see, right, is the color that we see is the complementary color to the light being absorbed. And you typically want to set your wavelength to the maximum absorbance when you're doing these type of experiments. So for example here, and I think it's filled out on your paper, so we'll just kind of go through the calculation here. The absorption maximum for the complex ion occurs at 470 nanometers. What is the color of the complex and what is the crystal field splitting? So as I was just mentioning before, we do see the complementary color to the light being absorbed. So if the maximum absorbance is over here, we would see the complementary color to it, and our solution would look orange. That is why when you did the red Kool-Aid or even our experiment with the equilibrium constant, where our solution was red, we set the wavelength in the greenish area there. And that is the complementary color to what's being absorbed in that case. We again could use this, which is really the energy, and this is Planck's constant. That is the speed of light, and that is our wavelength converted into meters. And that gives us basically 4.23 times 10 to the minus 19 joules. That's actually joules per atom. So if we want joules per mole, we would use our friend Avogadro's number, and we would multiply it by Avogadro's number, which are atoms per mole, and that will get us to joules per mole, and if you convert it to kilojoules per mole, will get us to 255 kilojoules per mole in this case. So this is a very similar calculation to one that you've done previously. Again, just kind of using Avogadro's number here at the end to convert it to moles per mole by doing so. Questions on that there? So let's talk about how do we know how the splitting is going to occur in this case. And it is based off of what ligands are present. This is a spectrochemical series. And on one side, we have strong field ligands. And strong field ligands will cause a big separation, a large separation between the lower and the upper d orbitals. Over here we have weak field ligands on the left, and these will cause a much smaller separation between the upper and lower d orbitals. And again, that kind of difference will basically account for how the electrons will go into the atom and how they will pair off. So if we take a look at some in the middle, it can go either way, and sometimes you'll be told, like, do it for the high spin complex or do it for the low spin complex, are treated as strong field or weak field. So sometimes they will give you some information about those in the middle. And I'll be honest with you, sometimes it may not even matter based on the number of electrons you're going to distribute. So for example, if you are only distributing 3 electrons, they're never going to get to the top no matter what you do because you only have 3. They're always going to, so it doesn't really matter the splitting if possible as well. So let's take a look at one here. Let's take a look at the we'll do the first. So if we take a look at this complex ion, first off, we do see the coordination number here is going to be 6, as obviously that is going, and that's basically the d orbital, where we have the lower d orbital. So what we want to figure out is what is the charge here on the nickel, and -1, there's -6. The overall charge is -2. That means that our nickel here would hold case. balance it out to that -2. If we look on the periodic table, nickel is number 28, which means if we write the electron configuration for nickel, that's going to be argon 4s2, 3d. I don't know where we got there. 1, 2, 3, 4, 5, 6, 7, 8. 3d8 in this case. Now, with it being nickel with a +4 charge, remember that these are transition metals, right? So they are going to dump the S's first, and that is going to be 2 electrons. We still need to dump 2 more electrons out of here. So that is going to leave us at argon 3d6 in this case. So it is these 6 electrons that we have our nickel here that we have to sort of distribute here in our crystal field splitting in this case. So again, if we come back here, we could see that bromine or bromide is a weak field splitter. And and x squared, y squared, and z squared that way. All right, so the way this is going to happen in this situation because of that splitting, we're going to distribute those 6 electrons. We're going to go 1, 2, 3. Once again here, this is going to be a weak field splitting of the bromide. And that means that the upper orbitals are not too far up there, so they'll just go in like normal. And we'll then down and pair off down here. So at this point, what we end up with is a very common question of what you're asked, which is how many unpaired electrons are there? And in this case, we got 1, 2, 3, and 4 unpaired electrons. This is going to give us a high spin complex because it is a lot more unpaired electrons than paired electrons. Any questions on that one there? Right. So why don't you try this one here and see what you come up with. Draw the crystal field splitting and see what you end up with here. The unpaired electrons in this case. All right, let's take a look since we're getting to the end here, just to kind of finish up this chapter here, since we're pretty much at the end. Let's take a look at this one, which was FeCN6 and -3, I believe. And obviously here again, we have cyanide, which is monodentate, and that is 6 of them. So this is a coordination number 6, which is going to give us our octahedral splitting, which is what we're looking at here. Our CN is -1, and there's 6 of them, which gives us a -6. Overall, it's -3. That means the iron is +3 in this case. And again, iron, which is 26, is argon 4s2 3d6 in this case, and it is with a +3 charge. We are going to get rid of these 2 electrons and take one of those out, and that's going to leave us an argon 3d5. So it is those 5 electrons that we want to distribute from iron into this picture. We do see CN in this case is a strong field ligand, which means when these go into populate, we're going to go 1, 2, 3, and they're going to go, this is kind of large in this case because of the CN minus, and it's not going to want to go up, so it will just continue to pair down here. We end up with only one unpaired electron in this case, and this would be what is again considered a low spin complex because of that. Any questions on that there? Yeah. I think you should generally just kind of know it. You would probably have one that would be, one end or the other, stuff like that. So it should be fairly not too hard to figure out, I think. Yeah. Other questions? All right. All right, so again, you can see the couple examples we just did there where we do end up with a high spin when we have a low, small splitting happening here, weak field. A strong field, we can get a larger splitting. And again, we get more paired electrons. Here for the octahedral is your different sort of arrangements that occur with 4, 5, 6, and 7 electrons. Again, on the left, high spins, small splitting, a lot more unpaired electrons, more paramagnetic. And here, a lot more paired electrons, low spin happening in a larger splitting that occurs. Now we also have this splitting that happens with a coordination number of 4 and tetrahedral geometry. It's the same splitting as the octahedral, but upside down, and works the same way. It obviously electrons will go low first and then to the high and then pair up. Again, if this is a large splitting, they will stay down here before they go up. If this is a small split, then they will kind of go one at a time and come back and pair up. So it's fairly similar to the octahedral, just upside down, basically reversed. You got the squared guys on the bottom. You could also have this for a coordination number 4, which is square planar, and you get a little bit more wacky splitting happening here. But again, kind of works the same way, going to feel lowest to highest to do so. For us, you are responsible for tetrahedral splitting and octahedral splitting, which is what we were looking at previously. So those two, which are basically the same, just one's up and one's down, are the two that you are responsible for. We will leave square planar off the board as there's a lot of different boxes to play with. Any question up there? That wraps up